Okay, so we're going to go on to the last topic, and that is kind of a special case scenario that this is kind of why we needed to do this unit before we moved on to some more astrophysics units, because I want to use this special case scenario in the future. So this special case deals with if no work is being done to or by the system, then our work value in the previous equation that we were just using is equal to 0. And so if we have the total mechanical energy initial plus the work equals the total mechanical energy final. If this value is 0, it simply becomes the total mechanical energy initial equals the total mechanical energy final. If we expand that a little bit, then we can just say the potential energy initial plus kinetic energy initial must be equal to the potential energy final plus the kinetic energy final. And this is our new equation that will eliminate work. And it's just the total mechanical energies initially and finally being equal to each other. If this is the case, if there's no work being done to or by the system, then we can state that energy is conserved, okay? Meaning that energy is neither created nor destroyed. Whatever energy you put into the system initially is the exact same energy that comes out of the system after at the end of the process, okay? That little video is of it's the famous, the bowling ball and a pendulum where the guy holds it to his face, lets it swing, and then it comes right back and just to the point where he started it initially, and it will never touch the teacher's face because of energy conservation, okay? Total mechanical energy being conserved. So, energy cannot be created or destroyed. However, it can be transformed, okay? And so the transformation of energy here just means we're taking energy that was potential and transforming it into kinetic, or energy that was kinetic, transforming it into potential energy. Okay, and you can think of this kind of classic example of a roller coaster. We're using that a lot here. But if you think about a roller coaster, at the top of the roller coaster, it has high potential energy because it's very high at the peak of the roller coaster track. And it's got usually very low kinetic energy because it's not moving very fast. But then as the car goes down the roller coaster track, it gains kinetic energy and it loses potential because it's gaining speed, all the while losing height. And so when that car is at the bottom of the track, it's got the maximum kinetic energy, but the minimum potential energy. If it would go back up just a little bit, like this track does in this example, it still has high kinetic energy, just a little less than the maximum. And it's still got low potential energy, but just a little more than the minimum, okay, in the previous picture. All right, so let's see if you can, all we have left to do is these example problems. So if you want, pause it here and try the last two problems on your own, and I will give you the answers. So in this first one, we have a ball at the top of a little incline, but it's set up there with potential energy of 100 joules, and the kinetic energy is 0 joules. And so we know right away that it must not be moving because it has no kinetic energy. So then we're going to release that ball, and it's going to go down the slope. It says the potential energy is 50 joules, and it wants you to calculate the kinetic energy. So the initial total mechanical energy in this case was 100 joules plus 0 joules. And then in our first scenario, after it goes down that first slope, the potential energy is now cut to 50 joules, and we want to get the kinetic energy, and so of course it's got to add up to equal 100, so the kinetic energy would be 50. So that would be blank A would be 50 joules. Then it's asking for the velocity of the ball at that point. So we know our kinetic energy is 50 joules, and that's equal to 1/2 mv squared, because that's our equation for kinetic energy. Solve for v, and I get about 7 meters per second for blank B. Then we're going over to C, D, and E, and if you see, it's just the ball is at the same height as the last section. So being that it's at the same height, that means the potential energy has to be the same. So the potential energy for blank C would also be 50 joules, meaning the kinetic energy for blank D also has to be 50 joules because they have to add up to 100. Energy is being conserved. The total energy of 100 joules will not change throughout this entire process. You can calculate the velocity based on the kinetic energy being 50 again, and you'll get the same velocity for blank E as you got for blank B of about 7 meters per second. Okay, then we have two last scenarios. One on the left where the ball just drops straight down from the cliff, basically, and then the far right where it went down the cascade of slopes to get to the ground level. Now, both of these balls are on the ground, so the potential energy in both of these scenarios would be 0 because it's right on the ground. The height is 0. So blank F and I, the potential energies are 0, meaning the kinetic energies for blanks G and J have to be 100 joules. If you set up this equation then to solve for the velocity of that ball at the bottom, set it equal to 100 joules for the kinetic energy and solve for V, you should end up getting 10 meters per second. Okay, and that all of those calculations were just using the 2.0 kilogram ball from the problem. All right, the next one, number 2, we're trying to calculate the velocity of the 50 kilogram ski jumper at points A, B, C, and E. Okay, now part A, so I'm still gonna keep up this overall equation for the conservation of energy where the total mechanical energies are the same initially and finally. But we're just looking for the velocity. Now the velocity is only associated with kinetic energy. Now if you see at all the points A, B, C, D, and E, the kinetic energy plus the potential energy is always 50,000, right? And that's because of this equation. So it can never change. It can never deviate from 50,000. We can just transform that energy from either kinetic to potential or potential to kinetic. So that's what you see going on here. At the beginning, point A, it's all potential energy because the skier is not in motion. Kinetic energy is 0, therefore the velocity at point A has to be, 0. Then we'll go on to point B. The skier is moving down the hill. The kinetic energy here is 20,000 joules, equal to 1/2 times the mass of the skier times the velocity squared. If you solve for that velocity at point B, I get 28.3 meters per second at point B. Then we're going to go down to point C. This is right before the jump there, where the kinetic energy is now at 35,000 joules. So instead of this 20, we now have 35,000. And so we're going to have a higher velocity because it's got more kinetic energy, and it's going to be 37.4 meters per second. Then he goes through the jump. That's at the top of the jump. It's part D. And then we're going to get the velocity or the speed of the ski jumper right as they hit the ground. All of the energy, all of the total mechanical energy has now been transformed into kinetic energy. And so now we can put kinetic energy equal to 50,000, set that equal to 1/2 mv squared and solve for v. And we get a final velocity of 44.7 meters per second there, right as the skier hits the ground. And so the last question is, why don't we need to calculate the velocity at point D when the ski jumper is actually in the air? And hopefully you can see that if the height of the skier at part D is equal to the height of the skier at any other point during their ride, then the kinetic energy will be equal, and the speed of the ski jumper will also be equal. So if you can see part B, or the section B of the ski jump, and section D, they have the same kinetic energy, so the speed of the skier would be the same at 28.3 meters per second. All right, so this is the end of the notes packet. Hopefully you can get through this and then start on the problem set that will be posted. And don't forget about office hours. We can do the problem set together or answer any questions you may have about this lecture. All right, good luck, guys.